Good day everyone, this is Engineer EMV and welcome to my channel. Before we proceed, hit the like button and subscribe for more civil engineering topics and practice problems in my channel. Welcome back guys. So in this video we are going to solve our second problem involving design of singly reinforced beams. Stated in the problem, it has a 5-meter long span beam simply supported at both ends and has a service dead load of 16 kN per meter and a live load of 14 kN per meter. It is placed uniformly along the beam. The base is 300 millimeters. It has an effective depth of 380 millimeters, compressive strength of 30 megapascal. The height of the beam is 450 millimeters. The length, of course, 5 meters, and the yield strength of the steel is 415 megapascal. Our specific gravity of concrete is 2.4. But the first question is, we need to find the value of our ultimate moment based from our loads. Next is to find the number of 16 millimeter diameter bars if the given ultimate moment is 200 kilonewton meter. And lastly, find the number of 16 millimeter diameter bars if there is an ultimate concentrated load at the midspan of the beam with the same dimension and same length. So first, let us solve for our first question. Based from NSCP 2010, also similar to the NSCP 2015, to solve for the factored value, we need to use the basic dead load and live load combination of 1.2 dead load plus 1.6 live load. We need that to solve for our ultimate distributed load or our factor distributed load. But first, we need to find the value of our total dead load. Our total dead load is composed of 16 kN per meter service dead load plus, of course, the self-weight of the beam. So to solve for the self-weight of the beam, we have a given of specific gravity of concrete is equal to 2.4. So to solve for its weight per linear meter, the formula is specific gravity multiplied by unit weight of water multiplied by the area of the cross-section of the beam. And that will be our formula to solve for the self-weight of the beam. So 2.4 multiplied by 9.81 if the unit weight of water is not given by default. And our area will be 300 divided by 1000 times 450 divided by 1000 to change it into meters. So for our self-weight, we have a value of 3.17844 kilonewton per meter. So solving for our factored distributed load, 1.2 multiplied by our service dead load 16 plus the self-weight 3.17844 plus 1.6 multiplied by our live load 14 kilonewton per meter. So our factor distributed load or our WU is equal to 45.414 kilonewton per meter. So next we need to solve for our ultimate moment in the beam. So in this case, we have a distributed load in the beam, simply supported, so we can use the formula WU L squared over 8 to solve for the maximum moment in the beam. So by substituting our values, WU is equal to 45.414 multiplied by the length 5 meters squared divided by 8, and we will get a value of 141.92 kilonewton meter. And that is the answer for the first question. So the next question is, we are going to find the number of 16 millimeter diameter reinforcement bars if our ultimate moment is equal to 200 kilonewton meter. So we are going to design the beam based on this given ultimate moment or a design flexural strength. So by recalling our previous steps in the previous video, we need first to find the Rn or the coefficient of resisting moment, and the next step is to find the theoretical or the required reinforcement ratio, and then we need to compare its value from our minimum and maximum reinforcement ratio values. So first, let us set our limits and solve for its values. So our raw min 1 is equal to 0.25 square root of fc prime over fy, and substitute our values. We get a value of 0.0330. And for the raw minimum 2 is equal to 1.4 over fy, we can get a value of 0.003373. So we can observe that the value of the raw minimum 1 is less than raw minimum 2, in which it should not be less than the raw minimum 2. So we are going to use the governing minimum reinforcement ratio equal to 0.003373. So to solve for the maximum reinforcement ratio, we use the formula 3/8 0.85 beta 1 Fc prime over Fy multiplied by dt over d. So before that, we need to solve for our beta 1. Looking at our given, the compressive strength of the concrete is 30 megapascal. So first, we need to solve for its value by this equation. 0.85 minus Fc prime minus 28 divided by 7 multiplied by 0.05. And substituting our values, we can get the value for beta 1 equal to 0.836. So to solve for the maximum reinforcement ratio for tension-controlled singly reinforced beam, it is equal to 3/8 of 0.85 multiplied by 0.836 multiplied by 30 compressive strength divided by 415 yield strength of the steel multiplied by 1. Since we only have a single layer, so the ratio of dt over d is equal to 1. So our maximum reinforcement ratio, tension controlled for singly reinforced beams, is equal to 0.01926. Carrying over our values, the governing minimum reinforcement ratio is equal to 0.003373 and our maximum reinforcement ratio for tension-controlled singly reinforced beams is equal to 0.01926. So now we need to solve for our required reinforcement ratio before we can compare it to our limits. So our first step is to solve for Rn, or our coefficient of resisting moment. We can solve it by using the formula mu over phi bd squared. So substituting our values, our mu is 200 multiplied by 10 raised to 6 to change it into Newton millimeter divided by phi 0.90 divided by phi bd squared. And take note that we are going to use a value of 0.90 for the reduction factor or phi since we are designing beams, multiplied by 300 for the base and 380 for the effective depth. So the value of our Rn is equal to 5.129783, or we should store it in any variable in our calculator so that there will be no discrepancy in our solution. So in this case, I will store it at A. So now we proceed to solving the value of the required reinforcement ratio. So the formula is 0.85 Fc prime over Fy, all multiplied by 1 minus square root of 1 minus 2Rn over 0.85 Fc prime. So by substituting our values, you use A because we stored the value of Rn at A. So for the required reinforcement ratio, or rho required, we can get a value of 0.01394. So our next step now is to compare it from the limits. So let's check. Our raw required is obviously greater than the raw minimum, so it is okay. And our raw required is also less than the raw maximum, and it is also okay. So we can say that the raw required is within our limits, so it is okay to use the value. It is under singly reinforced beams. So we proceed now in solving for the required area of reinforcement. So the formula is AS is equal to rho BD. So we are going to use the value of the rho required since it is qualified for the singly reinforced beam, multiplied by the base and the effective depth. So the value of our AS is equal to 1,589.482 square millimeters. So to solve for the number of bars needed using 16 millimeter diameter, we simply divide the required area by the area of a single bar. So AS over AB. 1589.48 divided by pi over 4 times 16 squared, we can get a value of 7.905. So by rounding up, our answer will be 8 pieces of 16mm diameter bars. And that is the answer for the second question. For the final question in this problem, we have our beam with a similar length of 5 meters, similar support, simply supported at both ends, but different in loadings. We have a factored concentrated load at the midspan of the beam. Pu is equal to 50 kilonewton. We need to find the number of 16mm diameter bars to carry the following load. So first we need to find the value of the design flexural strength based on the external load. So in this beam, simply supported with a concentrated load at midspan, we can use the formula Pu multiplied by length divided by 4. So our Pu is equal to 50. The length is 5 meters in total divided by 4. So our design flexural strength is equal to 62.5 kilonewton meter. So from here, we are going to use this value to determine the required area of the steel. So back to our step-by-step process. First, we need to solve for Rn. It is equal to mu over phi bd squared. Mu is 62.5 multiplied by 10 raised to 6. Again, to change it to Newton millimeter, our phi is 0.90. The base of the beam is still 300 and its effective depth is also still 380 squared. So the value for our Rn is equal to 1.603. And don't forget to store it in any variable in your calculator to avoid discrepancies. So next, solving for the raw required, use again our formula 0.85 fc prime over fy multiplied by 1 minus square root of 1 minus 2rn over 0.85 fc prime. So let's substitute our values. Our rho required is equal to 0.003992. So now let us compare it again to our limit. Our rho required is obviously greater than the minimum and also it is less than the maximum. So it is within the range of singly reinforced beams. Now let's proceed in solving for the required area using the formula AS is equal to rho BD. Our rho is our rho required multiplied by the base 300 and the effective depth 380. So the value for our area of steel is equal to 455.145 square millimeters. The next step, solving for the number of pieces, simply AS over the single area of 1 bar. 455.145 divided by pi over 4 multiplied by 16 squared. So the number of pieces is now equal to, by rounding up, we can get a value of 3 pieces. It can hold our design flexural strength of 62.5, and that is the answer for our third question. That's all for this video. I hope you've learned something. And if you have questions, inquiries, and topics in mind, just comment it down below. And let's see what will be our next topic in our next videos. Don't forget to hit the like button and subscribe for more civil engineering topics and practice problems by Engineer EMV.